Hi, welcome back to Elasticity. Last class we looked at the basic boundary value problem for elastic bodies. Let's see if we can get that. There you go. So find stress and displacement such that the equations of equilibrium are met and the constitutive equations are met. This has to be inside the body. So equations of equilibrium and constitutive equation have to be met inside the white part of the potato. You remember the continuum potato? It has to be met on the white part of the potato. The boundary conditions have to be met. The boundary conditions have to be met in the yellow part of the potato. You got it? Right? So it got a little bit messed up, but you've seen that before, right? So now we are going to look at certain characteristics of the solution. And we will exploit that to find approximate solutions, to do calculations, all kinds of things. So in order to do that, we are going to start with what is called the potential energy. So given any kinematical admissible displacement field, its potential energy is given by integral over the region of 1/2 Cij KL epsilon ij epsilon KL. This is the strain energy plus integral B dot U. This is the potential energy of the body force minus integral T dotted with U dA over the d omega 1. This is the potential energy of surface traction. So epsilon ij ui comma j plus uj comma I divided by 2. That's what this is. Okay. Cij KL is stiffness matrix, which is the inverse of the S matrix. Okay, so this is called the potential energy, and the Castigliano's first theorem says among all kinematically admissible displacements, the actual displacement minimizes or makes the potential energy stationary. In other words, partial PE with respect to displacement must be equal to 0. This is our minimum criterion. Now we are not going to show that in fact if this condition implies equations of equilibrium, strain displacement relations, strain stress relation, the Hookean relation, and boundary conditions. All of them are hidden in this one statement. Can you see how powerful this statement is? This is the starting point for all FEM programs. So rather than solving the original equations, they will try and find kinematically admissible displacement fields through their idea of finite elements. That's what finite elements do. They pick polynomial displacement fields that satisfy the boundary conditions and try to minimize it. You may not get the absolute minimum. The closer you get to the minimum, you can say the closer your solution is. Okay, so that's how kinematically admissible displacement fields work. So now let us look at the next one. So, before we go, let us look at an example. So I'm going to look at an example in a completely different field, which is in a spring mass system. So I have a spring, I have a mass hanging from it, and then I have a force F acting on it. Question is, how much is the displacement? I can do it by doing equilibrium equations. Equilibrium will give you mg F, and then this one will be kx. So you will get kx equals F plus mg. So x equals F plus mg over k. We know this, right? I can also do it by looking at the total potential energy of the system. So if it moves down by x, its potential energy will be half kx squared minus mgx minus fx. So this is potential energy of the body force, potential energy of the contact force, this is the potential energy of the spring. So then I do ddx, and lo and behold, I'll get kx minus mg minus f equal to 0, which implies this. So any statics problem for an elastic material you can always solve by minimizing the potential energy, or at least extremizing it, finding a stationary point. I didn't check the second derivative now, so I'm not sure whether it's minimum or maximum. This is actually a very powerful result, and it extends to nonlinear elasticity. It can be large deformation, all kinds of things. The potential energy will be different, but the procedure will be the same. Okay.